Let us discuss one important aspect related to evaluation of double integral, that is change of order of integration. Suppose we have got an integral of the form integral x is equal to a to b, integral y is equal to psi x to eta x, f of xy dy dx. We notice that here y is having variable limits and x is having constant limits. Can we convert it into the form integral y is equal to c to d, integral x is equal to py to qy, f of xy dx dy. That means here x is having variable limits and y is having constant limits. If at all we can change integral of one form to the other form or vice versa, then it is known as change of order of integration. So, to be brief, I can as well say that if we are having variable limits for y and constant limits for x, then converting it to an integral wherein x will have variable limits and y will have constant limits or vice versa is known as change of order of integration. Why shall we think of change of order of integration? Sometimes integration becomes easy when we change the order of integration. There is another aspect. Sometimes the integral as it is cannot be evaluated in its original form. That means if you have got a function of x and y, we may not be able to perform integration with respect to y, but when we change the order of integration, it can be integrated with respect to x. This is another aspect of change of order of integration. Let's now discuss a couple of problems based on the change of order of integration. Change of order of integration. The problem is like this. Change the order of integration and hence evaluate integral x is equal to 0 to infinity, integral y is equal to 0 to x, x e power minus x square by y dy dx. We may as well notice that because of the presence of y in the denominator of the exponent of an exponential function, we cannot evaluate the integral. That means we cannot integrate with respect to y. Then what shall we do? We shall change the order of integration. For changing the order of integration, let us observe the region of integration. The region of integration is as shown in the figure. Here y is equal to 0 means x-axis is the lower boundary, y is equal to x is the upper limit. That means the line making pi by 4 angle with positive direction of x-axis or y-axis is the upper limit. That means the region lying between the horizontal line and the slant line is the region. Here x changes from 0 to infinity. At origin x is equal to 0. As we move away from origin along the positive direction of x-axis, x can go to infinity. So that is the way in which the region is described. Let us describe the same region in a different way. Let us try to see that the region lies between two horizontal lines. One is y is equal to 0 or x-axis and another horizontal line at infinity given by y is equal to infinity. Then as far as x direction is concerned, there is a curve at the left hand side given by x is equal to y and another curve at infinity described by x is equal to infinity. So the region can also be described by the inequalities 0 less than or equal to y less than or equal to infinity, y less than or equal to x less than or equal to infinity. So by change of order of integration, given integral becomes integral y is equal to 0 to infinity, integral x is equal to y to infinity, x e power minus x square by y dx dy. Now we can integrate this with respect to x. We can as well get integral y is equal to 0 to infinity e power minus of x square by y divided by minus 2 by y. This quantity to be evaluated at x is equal to y and at x is equal to infinity multiplied by dy. E power minus infinity is 0, e power 0, e power minus y is the other quantity, so we get half of integral y is equal to 0 to infinity y e power minus y dy. On integration with respect to y, we get half of y times minus e power minus y minus 1 into e power minus y to be evaluated at y is equal to 0 and infinity. We know that e power minus infinity or e power minus y as y tends to infinity is 0, e power 0 is 1, y times e power minus y also tends to 0 as y tends to infinity. So, simplified result becomes 1 by 2. Let's discuss another problem on change of order of integration. The problem is like this. Change the order of integration of integral 0 to 1 integral x square to 2 minus x of xy dy dx. Change the order of integration and hence evaluation. Here the region of integration is y is equal to x square. That means it is a part of the parabola in the first quadrant. Y is equal to 2 minus x or x plus y is equal to 2 is a straight line passing through 2 0 and 0 2. Naturally, the region of the almost triangle looking region is bounded by x is equal to 0 and x is equal to 1. The straight line and the parabola intersect at 1 comma 1. So, after observing the region of integration, we notice that it is to be divided into two parts, R1 and R2, where R1, the lower portion as shown in the figure, is described by 0 less than or equal to y less than or equal to 1, 0 less than or equal to x less than or equal to root y, because it lies between two horizontal lines y is equal to 0 and y is equal to 1. It is bounded by two curves. One is the y-axis at the left described by x is equal to 0 and the parabola described by x is equal to root y at the right side. Now R2, it lies between y is equal to 1 and y is equal to 2. It lies between y-axis, that is x is equal to 0 and the straight line x plus y is equal to 2 or x is equal to 2 minus y. So the inequalities describing the region R2 are 1 less than or equal to y less than or equal to 2, 0 less than or equal to x less than or equal to 2 minus y. So when you change the order of integration in this problem, given integral is to be written as the sum of two integrals. One is over the region R1 and the other is over the region R2. So integral over R1 xy dx dy plus integral over R2 xy dx dy. Let us write the appropriate limits. So that is equal to integral y is equal to 0 to 1, integral x is equal to 0 to root y xy dx dy plus integral y is equal to 1 to 2, integral x is equal to 0 to 2 minus y xy dx dy. In both integrals, we have to perform integration with respect to x first. So the first integral becomes integral y is equal to 0 to 1 x square y by 2 to be evaluated at x is equal to 0 and root y dy plus the second integral, integral y is equal to 1 to 2, integral of xy this time is x square y divided by 2 to be evaluated at x is equal to 0 and 2 minus y dy. Substituting the limits, we get half of integral y is equal to 0 to 1 y square dy plus half of integral y is equal to 1 to 2 y into 2 minus y whole square dy. Now to perform integration, we get half of y cube by 3 to be evaluated at y is equal to 0 and 1 plus half of 2y square minus 4y cube by 3 plus y to the power 4 by 4 to be evaluated at 1 and 2. Substituting the limits and doing little simplification, we get 1 by 6 plus 5 by 24, or on further simplification we get 3 by 8.